in and find their values in order to be able to compare which one is less, which one is more. Now, what we saw when we were solving quadratic inequalities, that quadratic inequalities looked like these, some sort of a parabola, and we would be comparing them to zeros, right? One of our very first step was to manipulate it in such a way so that we have our function compared, whatever the symbol is, greater, less than, doesn't really matter, to 0. And that gave us an advantage. They gave us an advantage. We still had to find those points, those, as they're called, zeros or X-intercepts, where the function crosses between positive and negative values. But when we were plugging in points in this region, for example, I didn't care what the value was, or let's say this region, I didn't care whether this is -3 or -3, 33.7 or -371. I didn't care. I just cared that it's negative. If it's negative, I knew it's less than 0. If it's positive, I knew it's greater than 0. Comparing to 0 is much, much easier than comparing two values, because when you're comparing two values, you have to find each value and then make a decision which is the bigger or which is the smaller value. Whereas comparing a function value to 0 is easier, I guess, let's say, easier, because if your function value is positive, well, then you know positive is greater than 0, right? If your function value is negative, well, then you know negative is less than 0. Don't care if it's -7 or -7,000, you know it's less than 0. So it's a much quicker process. That's why oftentimes when we're solving inequalities, we want to rewrite them in such a way to be able to compare them to 0, as opposed to comparing a function to another function or even a number. So that's one little part that we're going to notice in both of these types of inequalities. Now let's start with polynomials. Polynomial inequalities. We introduced polynomial functions. We know how their graphs look. So if I have a graph, which is a smooth curve, right? This would be an example of a graph. These are some points on the graph. For example, here, my graph is negative, right? Here, my graph is positive. Then again, negative. And here it stays negative, right? Now, the only way that I can go between positive and negative, between being above or below the x-axis, is if I go through a 0, through an x-intercept. I cannot be doing something like this and all of a sudden jump up here. A polynomial does not behave in that way, right? It's continuous and it is smooth curve. So the only way that I can go between positive and negative is if I'm passing through a 0, through an x-intercept. So that's an important note to make. Polynomial can change between positive and negative only at x-intercept, or what we call the 0 of the polynomial, the real 0 of the polynomial. It doesn't have to, polynomial doesn't have to change between, right? Because we see here, we have a 0 here. It was negative. It remained negative. It tells us something about the multiplicity of that 0, so we can use that to our advantage. But if a polynomial changed from positive to negative or negative to positive, it can only occur here. It can only occur at an X-intercept. So that's an important observation, and it is not true for rational functions. We will see that when we get there. But now, knowing these things, let's discuss the steps that we would take in order to solve a polynomial function. First step is to get that 0. So we're going to rewrite the polynomial my writing is way off. Polynomial inequality in the form P of X, and then whatever may be the symbol, I'll just use greater than, so I don't have to write all 4 of them, 0. But again, the key is that guy, 0 on your right hand side, and whatever is on the left hand side, that will be considered your polynomial function. So you're comparing your polynomial function to 0. That was this discussion here. We want to compare a function to 0 because it's easier. It's not the only way, but it's easier way. So that will be our step 1. Step 2 is we have to find those points where we can possibly change between positive and negative values, and those are the X-intercepts, or the real zeros. So we will say find real zeros of P of X by solving the equation P of X equals 0. That's how we find X-intercepts, which is synonymous with real zeros. So that'll be our second step, find those boundaries where we might cross. We don't have to cross, but we might cross between positive and negative values. Step 3 will be to create a sign analysis chart. Create a sign analysis chart. That's what I refer to it as. And the sign analysis chart is basically the one-dimensional version of this. Instead of doing two-dimensional graph and saying, here's how high we go or how low we go, or at least even estimating, we say, here's where our zeros are. And then based on various things, let's figure out each interval, whether we have positive function values or negative function values at each of those intervals. And we want to use everything we have at our disposal. So we want to use end behavior. We know this thing called end behavior of polynomials. And we also want to use multiplicity of our zeros, right? Because that'll help us speed the process up, or you could plug in points. Plugging in points will still work. If you want to test out a point in each region, that's perfectly fine, but I think this will be quicker. Once the sign analysis is complete, you need to answer the question. You need to answer, so write interval notation. Your final answer is the interval notation. And if you're answering the question where P of X is greater than or equal to 0, then that means you want the positive regions of your sign analysis chart. If you're answering the question where the polynomial is less than 0, then you want the negative regions of your sign analysis chart. And you also have to, of course, remember for interval notation where you use brackets or parentheses. So all that comes back here in play. But that's really it. Those are the 4 steps that we will have to accomplish, and that'll solve every polynomial inequality. So we'll do a couple of examples for that, and I'm going to try and find a good one that I like. I think I like 30. So for 30, we have x to the 4th is less than 9x squared. So in theory, we could say the following. Let's just compare this as function f to this as function g, and find points where they intersect, and then look at each region, see how they behave. But that's a lot more work than doing what we're about to do, which is first move the 9x squared to the other side in order to create this 0 on the right-hand side. This is my p of x. So that guy here is my polynomial function. My p of x is equal to x to the 4th minus 9x squared. So now instead of comparing 2 functions to each other, I'm comparing this new function, which is a polynomial, to 0. And again, comparison to 0 is much easier. That's why we choose to do that. And the steps are we have to find x-intercepts. Right? And when we're looking for x-intercepts, the equation to solve is p of x equals 0. So all these things we were using, they're coming back. We're going to be using a lot of things. That's how math is. It builds on top of each other. Each section somehow uses not everything, but a lot of things that we've already established before. So my p of x is this x to the 4th minus 9x squared. I have to solve the equation for x, of course, and this is factorization. We would like to factor this by taking the GCF out. GCF is x squared, leaving me with x squared minus 9. And we will factor it all the way. We have x squared, x minus 3, x plus 3. And I get 3 zeros. 3 real zeros. One of them is x is equal to 0. One of them is x is equal to 3. One of them is x is equal to negative 3. Let's also note their multiplicity. X equals 0 came from a factor with exponent 2. So this is even multiplicity. Multiplicity of 2, but again, even multiplicity. X equals 3 came from a factor with exponent 1, odd. X equals negative 3, also odd multiplicity. Next is the sign analysis chart. For the sign analysis chart, I have 0, I have negative 3, and I have positive 3 as my points. And I will mark them as closed circles, and I'll explain the reasoning a little later. Because they're, well, I guess I'll explain it now. I'll mark them as closed circles because these are actual points on the graph. They exist. They're not asymptotes or any other type of entity like a hole that we will encounter in rational functions. So now we have options. We can either do what we used to do for quadratics and pick a number in each interval and plug it in. That's perfectly fine. You can do that, plug in a value, see if you get positive or negative result, put in a positive or negative corresponding interval symbol. But we have a better option. So let's use that. This P of X, we know it's even degree, right? Because the degree is 4, so it's even degree. And the leading coefficient is positive 1, so it's positive leading coefficient. What does that tell me about my end behavior? Do you guys remember? How would it behave on both ends? As we go to positive and negative infinity, what would my end behavior be for this polynomial?
Y approaches infinity.
Yeah, my end behavior would be that, right? So there were 4 cases for polynomials. Again, we talked about end behavior. If it's even positive, then it approaches infinity in both cases. So you might want to review those, but that tells me that as I prefer to start left to right, but then we will still compare that everything works. So again, this is going to positive infinity, right? What that tells me is this region then should be positive based on end behavior. Because if it approaches positive infinity all the way on the left, well, then all the way on the left is anything to the left of -3. It's got to be positive. Or you could plug in a point and confirm that it is going to indeed be positive. Then we start using multiplicity. What is the multiplicity of -3? Odd or even?
Odd.
It's odd, therefore I have to cross, which means as I cross -3, I have to go down to negative. Then I reach another X-intercept. What is the multiplicity of 0?
Even.
Even. That means I bounce off of it. I stay negative. Then I hit another X-intercept, 3. That one is
Odd.
That one was odd. So I cross it. Therefore, I go from negative to positive, and that confirms my end behavior here, right? It confirms that my end behavior should have been positive on the other end. So if you bounced off of your zeros and then your end behavior doesn't match, you know that there's something wrong. So you definitely want to go back and check where you made a mistake, whether it was the starting point, the end behavior, or one of the bounces from the zero. Will this topic be on the exam or quiz? Both, and on the final? Yeah, I mean, I don't see why this topic would be different from any other topic. So yeah, this is part of our curriculum, sure.
Professor, I have a question.
Yeah.
When we say that endpoints are positive, can we just put in the endpoints like the end parts positive and everything that is left just put negatives?
No, because you could have options where endpoints are positive, right? But you can have, for example, 4 zeros and all odd multiplicity. So this would be positive, negative, positive, negative, positive, right? So endpoints are positive, but you can still have sign changes in between. So you gotta consider all of your tools there, all of your zeros and their multiplicities, and then confirm that it works out with the end behavior. So go through those steps and do either a bounce or cross from each X-intercept, and then make sure that when you come out the other end that it confirms with the end behavior. So in this case, it happened to be that they're both positive and between they're both negative, but not all the time, not always. And again, if you guys aren't sure, you can always plug in points in the intervals and confirm. But here we are. We have now our sign analysis chart. Our equation to, or rather, our inequality to solve is P of X, the polynomial, less than 0. So does that tell me I want positive or negative intervals?
Negative.
Tells me I want negative intervals. I'm only interested in the negatives. I'm not interested in these guys. Now I have these two negative intervals and they're actually right next to each other. If this symbol was inclusive, then I wouldn't even have to separate them into two intervals because they're right next to each other. But because this symbol is strictly less than, it tells me that my borderline points here are not included in the solution. So I do have to separate it into two parts. My first part is from -3 to 0, both not included, union, and my second part is starting right back up at 0 and going to +3. So that would be my solution set here. So it's pretty cool. Well, to me, it seems pretty cool that we can now use these multiplicities and end behaviors to save some time, not have to plug in point for every region. And that saves us a little bit of time. But again, if you have enough time on your quiz or on your exam and you want to make sure, you can always plug in points on the regions and make sure you have the correct ones. Let's do this as part B as well. So this is part A.
Professor, why can't you just say it's from -3 to 3?
The reason is this guy. If I say it's from -3 to 3, then I'm saying that x equals 3 is in there, right? I mean, not 3. X equals 0 is in that interval, right? But is x equals 0 a solution here? And the answer would be no, because when I plug in 0, I'll get 0. It's one of my X-Intercepts. I want strictly less than 0. I don't want equal to 0.
Got it.
So that's why we would have to split it up. If it were, so let's do a couple of different parts here just to show you guys the difference.
Professor, but if we have the case that it's less than 0, can we just write -3 to 3 or no?
Well, we do have the case where it's less than 0. Are you saying if we have the case
less
where...
or equal?
Yeah. So if this were the case, if it was less than or equal to 0, then we would just say from -3 to 3. We should not then split it up into two parts. I take that back. We should say -3 to 3 with those being included, right? -3 and 3 would also be included in there, right?
Okay,
but
thank you.
What if we... Is that a question? No. So what if we look at part C of this? What if we wanted to consider P of X is greater than 0? What if that was the inequality? Then we would have to say, well, the intervals are -∞ till -3, excluding it, union, and then +3 to +∞, right? So once we have the sign analysis chart, we can answer all kinds of various inequalities with that, just looking at the signs, the positive and negative. Okay. Let's have you guys try one. Pretty similar. Number 28. And these are, by the way, on page 229, if you're looking them up in the book. Here we have x cubed. Actually, no, I don't think that's the one that I want. Let me think if that's the one that I want. Yeah, that's fine. X cubed plus 2x squared minus 3x is greater than 0. So go ahead and take about 5 minutes or so. Follow those similar steps and set it up and solve it. All right, following those same steps, we will start by moving everything to get 0, but that's already done. So again, I will outline that this is our p of x, our polynomial function. And I'll just write it down on the side here. That's our p of x. And we have to find X-Intercepts by setting the function equal to 0. So this gives us x cubed plus 2x squared minus 3x equals 0, which we can factor. Anytime we have to factor, we start by GCF. Take out x squared plus 2x minus 3. This also factors nicely as plus 3 and minus 1. So we got 3 x-intercepts here. One is 0, one is -3, one is +1, and the multiplicity for each of them is 1, so they're all odd multiplicity zeros. Now we can do our sign analysis chart. So we have a 0, we have a -3, and we have a +1. These are my x-intercepts. We can either plug in a point, or we can look at the end behavior again of this polynomial. This is odd degree polynomial with a positive leading coefficient. So the end behavior of such polynomials looks something like that, right? It does whatever it does in the middle, but the end behavior looks something like that. So I know that all the way on the left portion, this should be negative. And all the way on the right, it should be positive, but let's see if we get that. Each of these zeros is odd multiplicity, so each one of them I should cross, meaning I should switch from negative to positive, or switch between positive and negative. So as I go left to right, from negative, I then would go to positive in this region, back to negative in this region, and back to positive in this region, which coincides with the end behavior that we were expecting. So far, everything looks okay. Again, if you prefer, you can plug in points. It should give you the same result, the same sign analysis. Now we have to find the actual interval, find the answer. So our interval, we're looking at p of x. We want it to be greater than 0, right? That's our p of x here. We want it to be greater than 0. Again, it's strictly greater, which means we're not including the boundary points. And this implies greater than 0 that we're looking for positives. So we don't care about the negative parts. We care about only the positive intervals. And to name the interval correctly, we will start at -3, not including it, get to 0, not including it, union, and then +1 to +infinity. That would be our final answer here. Any questions?
How did we get the negative value for in between 0 and 1?
So that's based on the zero's multiplicity, right? We know that if we're all odd, if all of our multiplicities are odd, then my function does something like this: has to cross, has to cross, has to cross. Right? So every time we have an odd multiplicity 0, that means our sign will switch. Every time we have an even multiplicity 0, means our sign will stay the same. So for odd, they switch. For even, they stay. based on what we discussed and when we were graphing polynomials.
It would switch between every point?
Between every positive, every odd zero.
Oh, thank you.
Because in the previous example, what we saw here, we didn't switch here. We went positive, we switched to negative, we stayed negative, and then we switched to positive. The reason is 0 here was even multiplicity. So again, it depends on odd versus even, things that we discussed on Tuesday or even earlier, I forget. So multiplicities of our X-intercepts. That's how we know. Good?
Yeah, thank you.
All right. Now let's get to the more difficult rational inequalities. These should be a little more fresh in our memory because, yeah, polynomials we did previous week, but rational functions we did Tuesday. So what we saw are the following possibilities. We can have vertical asymptotes. We can have horizontal asymptote or an oblique asymptote, but those don't really do a whole lot for us. I'll still graph one. So let's say we have this guy as well. And then we saw following possible scenarios. For example, our function can do something like that. In this region, it may do something like this in this region. And it may do something like this, have a hole, and continue on in this region. So here we have to consider a lot more options, right? If for polynomial, we can only switch between positive and negative when we hit a 0. Here, let's look. Here I have a 0, right? Let's do it with different colors. Let's do purple. So I have a 0 X-intercept or 0 here and here only, right? Those are the only two places where I have an X-intercept. I don't have one here because I have a hole there. Again, remember, a hole occurs if we can reduce out a factor, which otherwise would have given us some value in X-intercept and well, yeah, possible X-intercept or not X-intercept, but a possible vertical asymptote. So if I draw this, my function is positive here, and then my function is negative down there. And it crossed the 0 as we would with polynomials. But then, as soon as I cross over this asymptote, my function is again positive, right? This piece of my function is positive. But I never went over a 0. Instead, I went over a vertical asymptote. So that shows me not only X-intercepts, but also asymptotes may have us change the sign, right? From negative here to positive on that side. Then again, I encounter a 0. So this 0 again go to from positive to negative. So that we already know. We know that X-intercepts can do that to us. And then I have an asymptote again, but here I see that I went from negative to negative. I didn't switch from negative to positive. But we remember something about multiplicity of asymptotes as well, something we talked about on Tuesday. We talked about that odd multiplicity asymptotes behave similar to odd multiplicity zeros in a way that function values switch between positive and negative. Even multiplicity asymptotes, function values stay If they were negative on one side, they're negative on the other side. If they were positive on one side, they're positive on the other side. So in this case, this asymptote doesn't produce a sign change. But then we see another phenomena, which we probably won't run into in our examples here, but it is a possibility that we're negative and then we don't have a zero. However, we are positive after. But what we have here is a hole. No asymptote, no x-intercept, but a hole, a factor that got canceled out, that got reduced out. So that tells us that when we're picking up all these values to consider for our sign analysis chart, we have to consider x-intercepts, we have to consider asymptote, vertical asymptotes, let's be specific. Horizontal asymptote doesn't do anything for us. We wouldn't cross between positive and negative at horizontal asymptote unless it happens to be the x-axis. So x-intercepts, vertical asymptotes, and possibly holes if we run into those examples. That's where our function value, so those are those special points where function can switch between positive and negative. It doesn't have to, right? We saw zeros with even multiplicity, we don't switch. We saw that asymptotes, even multiplicity, we don't switch. So it doesn't have to, but it may. So those points have to be considered. All right. Other than that, everything else will be pretty similar. There's still some minor differences between polynomial and rational, but this is the main difference, that you're not only considering x-intercepts, you're also considering vertical asymptotes and holes. Let's list our steps. Step 1, we still want to rewrite the function in the form of r of x, and then again, whatever is your inequality symbol, I'll just put less than 0. So you want to compare it to 0. And for polynomials, it was pretty straightforward. We would just move everything to the other side. For rational functions, if you guys remember, rational functions are defined as p of x over q of x. So if we move one term to the other side, we would have two terms on the left side, and that's not the proper form for a rational function. We have to combine those two terms together. So sometimes you'll have to add rational expressions by finding their LCD and so forth, right? So we would have to have this form to be specific. One term on the left and then 0 on the right. Step 2, here we will actually break it up into two parts as well. Previously, we would just say find x-intercepts. Now we have to say find x-intercepts by letting the numerator equal to 0. So again, our function now has this form p of x over q of x. P of x is the numerator, so we're letting p of x equal to 0, because that's how we would find x-intercepts of a rational function. That's what we did on Tuesday. But the other part of this is to find vertical asymptotes They could be holes as well. So that's why it's important not to reduce your factors if you're solving a quadratic inequality, because if you reduce a factor and you ignore it and you don't mark it anywhere as a whole, then you would have lost out on the possible crossing positive and negative. So find vertical asymptotes, or they could be holes, and we do that by letting the denominator equal to 0. Denominator equal to 0, and using our notation, denominator here is q of x. So we would let q of x equal to 0. That would give us our vertical asymptotes and possible holes, whichever ones they would turn out to be. Then we have to make a note. Whatever points we find from this step, those x values are not to be included into the interval. The meaning behind that is they are still part of our interval. They're still our boundary points. But if we have a vertical asymptote there, then it's not a closed circle, it's an open circle. Because it's not part of the actual function. It's not a point on the function. It's not an X-intercept. It is either an asymptote, which means it's not a point on that function. It's not part of the domain, or it's a hole, which means it's the same thing. It's not a point on the function. It's not part of the domain. So those are going to be treated as holes. Therefore, when we will write our interval notation, we will always have a parenthesis there, never a bracket. Depending, of course, on where the interval is going, it'll be opening in one way or the other, but it's always going to be parenthesis for those values that we got from vertical asymptotes. We'll see what exactly that means based on an example soon. Step 3, create a sign analysis chart. We don't really have, well, we do have end behavior for rationals, but I don't think it's a quicker way than plugging in a point. You could use end behavior because end behavior here is your non-vertical asymptote, whether it's horizontal or oblique. And if it's not 0, then you should be able to figure out what the end behavior is if you want. But I think it's quicker to just plot a point. However, multiplicity you should still use. So use multiplicity, zeros, and asymptotes, because they behave similarly, and that'll save you a little bit of time. So you just need to plug in one point, and from there you can then use multiplicities in order to get each region. And finally, step 4, once you have your sign analysis chart complete, then you can go ahead and basically answer the question. So write interval notation, answer with interval notation, same thing. If your R of X is greater than 0, that means you want your positives. If your R of X is less than 0, that means you want your negative regions. So a lot of similarities between polynomials and rational inequalities. The main difference is where you can cross over. There's more places. There's also vertical asymptotes and holes. All right, so let's try and do a couple of examples and then I'll give you guys a break. First one, we'll pick something on the easier side. Which one do I like here? Number 40 I like. X plus 5 squared over x squared minus 4 is greater than or equal to 0. Step 1 for these, if it needs to be done, it's more complicated than polynomials. We'll see it on our next example, but in this example, step 1 is done. It's already 0 on the right-hand side. The left-hand side is already one term, so this is my r of x in this. And I'll just copy it over here. It's x plus 5 squared over x squared minus 4. That's my rational function. Step 2 is for me to find my intercepts and vertical asymptotes. For x-intercepts, we would let the numerator, right? Remember our numerator here, x plus 5 squared, we would let that equal to 0. That produces just one solution, x equals -5, but it has even multiplicity because it came from a factor that was squared. So even multiplicity. Not y-intercept, but asymptotes, wholes, that's where we would let the denominator equal to 0. So we have to solve x squared minus 4 equals 0. Pretty, again, easy. This one isn't factored, but it factors as x minus 2x plus 2, giving us x equals +2 or x equals -2 as our asymptotes. I'll just call them asymptotes. We don't really need to differentiate between a whole and an asymptote for inequality. For a graph we would, but not for inequality. And both of these are odd multiplicities. However, you have to remember these are asymptotes. They're not points on your graph, so they're not to be included in our intervals notation here. So now, yeah, question.
The denominator we use for the x-intercept.
I couldn't hear you.
I was saying for the denominator, do we only use the x-intercept? I'm sorry, yeah, for the x-intercept, do we only use the denominator?
So over here, I wrote that answer to that question. It says here, to find the x-intercept, you let the numerator equal to 0. To find vertical asymptotes, you let the denominator equal to 0. So for x-intercepts, we only use the numerator.
Wrote that down wrong. Sorry. Thank you.
No worries. And the reasoning for that, again, that was discussed on Tuesday, just because of how these rational functions work. So you'd need to review Tuesday's lesson to see how to find asymptotes and how to find zeros. And that'll bring you back to those two statements, basically. All right. So now we have our points on the graph here. We have -5, we have -2, and we have +2. But remember that they're different. -5 is an actual point. It's the x-intercept. So this has a point. -2 and 2 are asymptotes. There's no point there. They're open circles. Function is not defined at those values. They're asymptotes. So that's why I'll mark them with open circles in order to help me remember when I write my interval notation down. Then, again, I could talk about end behavior, and it's a good exercise. So looking at this guy, end behavior in this case would be a horizontal asymptote, right? What would be the horizontal asymptote here? What do you guys remember from Tuesday's lesson? You'd have to compare the degrees and then come to a conclusion, maybe do long division, maybe not. So what would be the x-intercept here? I mean the y, the horizontal asymptote. I'm throwing all
It'll
kinds
be
of...
the leading coefficients divided by divide by each other.
Yeah, it would be the ratio of leading coefficients because they're same degree. So in this case, what would it be?
0.
Can't divide and get 0. Leading coefficients are 1 and 1, so 1 divided by 1 would be 1. Again, this part, you don't really have to do it. You could. So if I know that my end behavior is 1, that tells me that I go to the left, my function is forever approaching 1, and as I go all the way to the right, my function is forever approaching 1. So it's positive. That's what I meant, that you could still look at end behavior, but we don't, I think that's more complicated. So I think it's quicker to just say, let's pick a point, plug it in, and see what we get. So let's pick a point in this region. Let's pick x equals -6, for example, plug it into our function and see what we get. So I'd go with that, and I think it's a little easier. So my function tells me -6 plus 5 squared over -6 squared minus 4. This is -1 squared. This is 36 minus 4, so this is 1 over 32. But again, we said that's the beauty of comparing to 0. Don't really care what value it is. We're not comparing to any other value. We're just comparing it to 0. So if it's positive, then it's, we already know it's bigger than 0, so it's positive. So that gives me a starting point here, and I know that this region, I am positive. Now we start using multiplicities. Here we have our multiplicities listed. -5, even multiplicity. Do I switch or do I stay?
Stay.
I stay.
Stay.
Even multiplicity stays positive. -2 is odd multiplicity. Do I switch or stay?
Which
And that one I switch. Yes, so I go now to negative. Then I get to +2. Again, it's odd multiplicity. Again, I would switch. So then I would go back to positive. Now I have my sign analysis chart complete. Again, if for whatever reason you're not too sure about your multiplicities and using them, plug in points. That'll give you the same pluses and minuses, but multiplicity is quicker. Next is to actually answer the question. So let's scroll back up and see what the question was. The question was, when is our rational function greater than 0? So that's what we're trying to figure out. When is our rational function greater than 0, which implies that we want the positive regions. So we don't care about this guy. We care only about the positive regions. Was it strictly greater or greater than or equal to? I already forgot. No, it's greater than or equal to. So that actually then changes things a little bit, right? So it's greater than or equal to. It still means we want positive regions, but it means that the X-intercept points are to be included in the interval. So in this case, these two intervals are actually joined together because we're including the point that would be their boundary. Otherwise, we'd have to split it up. If it was strictly greater, then we would have to split it up into two intervals and write it along the -5, not being included. But as is, I don't want yellow, I want red. As is, we would start at negative, and how is it? Oh, I think I have the highlighter turned on or something. I don't know. I guess it's slowly starting to freeze up again. So we would want -infinity all the way to -2. Now, the reason why we are not including the -2, even though our symbol is greater than or equal to, the reason why we're not including -2 is because the -2 is not a point, it's an asymptote. So the -2 has to be excluded. That's what that note meant in the steps. Then union, +2, again, +2 was an asymptote. We do not include it. All the way to +infinity. So that would be our answer here. All right. So I think what we will do next is, I think 46 is a good example, not too difficult. Or 48, more difficult one. That's fine. Let's do 48, the more difficult one. And then I'll give you guys your break. So on this one, what makes it more difficult is that we don't have 0. We have 5 over x minus 3. And here we have strictly greater than, and we have 3 over x plus 1. So we have to do a bunch of algebra before we can start doing all those sign analysis stuff. We have to get the right format first. And to do that, we need to move the right-hand side term over to the left side. We have to subtract it on both sides, giving us 5 over x minus 3 minus 3 over x plus 1 greater than 0. So that's how we get the 0. But we're far from done. We now have to combine these two rational expressions. So you have to remember your algebra skill here. You have to remember how to add or subtract rational expressions, and you would need LCD. In this case, our denominators are factored and prime. They have no common factors. They're relatively prime, as we could say. So we would need to multiply each one by the missing factor. And the missing factor for each one is the other one. So in this case, we're missing x plus 1. And in this term, we're missing x minus 3. Again, if you've forgotten how to add, subtract rational expressions, make sure you guys look up your algebra textbook, how that's done. Then we have our LCD, so we can combine them now with x minus 3. Why does it become 0? It's not 0. Let's see if I can. It becomes difficult. Oh well, we'll get rid of this guy, get rid of this guy. So this was x minus 3. There we go. So now we have x minus 3x plus 1 as the LCD. And we have 5 times x plus 1 minus 3 times x minus 3 greater than 0. Make sure you guys don't do something like this that a lot of people do in algebra class and pre-calc. That's unacceptable. If you do that, you, I don't know, might want to read a little more on algebra class to remember you can't reduce if you have multiple terms. Make sure you do not reduce at this stage. You would then distribute the 5. That would give us 5x plus 5. Distribute the negative 3 minus 3x plus 9 all over the LCD. greater than 0. Combine like terms. That's 2x plus 14. 5x minus 3x and 5 plus 9 over x minus 3, x plus 1 greater than 0. If you want, you can leave it like that, or you can, if you want, factor a 2 from the numerator. That's up to you at this point. But this is our rational function now. This is r of x, and it's equal to 2x plus 14 over x minus 3, x plus 1. So what we do now is we work with that version of the function. So all that was simply step 1. Again, a lot of algebra for step 1. That's what makes this problem more difficult. Step 2 is to find, well, it's not even right. Step 2 is to find X-intercepts. And not only that, but also to find the asymptotes. So for X-intercepts, whoa, what happened here? It's really tripping out on me now. All right. All right, I think what I'll have to do now is I'll have to give you guys a break and time to finish this one as well, and then hopefully it'll cool down enough for me to continue after that. So make sure you write down in your notes where we currently are. You have this 2x plus 14 over x minus 3 times x plus 1. That's our new form that we were after. And I'll have to turn this off for now. But let's put a time limit. Let's say 10 minutes. 10 minutes to try and finish this guy. And then let's say about, let's do 10. Yeah, I think 10 minutes for your break will be enough. So 20 minutes total. Let's say it's 8:15, so 8:35. 8:35, we're gonna continue back. And hopefully I cool down this guy, and then I'll have no problems. All right, so about 20 minutes for you guys to finish the question, and then also a break. So see you at 8:35.